Welcome back, my dear students. In this video, we will discuss three important classes of operators and its properties. The operators are self-adjoint, unitary, and normal operators. So, let T be a bounded linear operator on a Hilbert space. So, T from S to H is a bounded linear operator where H is a Hilbert space. Then T is said to be self-adjoint if T star is equal to T. That is, the adjoint operator of T should be equal to T itself. That is, inner product Txy should be equal to inner product x T star y, which is the definition of adjoint operator, and x Ty whenever T is self-adjoint. So whenever T is self-adjoint, its adjoint operator and the operator should be same. And the bounded linear operator T from a Hilbert space onto itself is said to be unitary if T star is equal to T inverse. That is, its adjoint operator is the inverse of T, which can, from the definition of inverse, which can be only defined if T is bijective. Otherwise, T inverse does not exist and T star is equal to T inverse has no meaning. So, a bounded linear operator T from a Hilbert space H onto itself is said to be unitary if T is bijective and T star should be equal to T inverse. Or in other words, inner product Txy which should be equal to x inner product x T star y which should be equal to x T inverse y inner product. And the Hilbert, the bounded linear operator T from H to H is said to be normal if T star should be equal to T star T. Okay. Or the adjoint operator of T and the operator T commutes. If the adjoint operator T and the operator T commutes, that is T star is equal to T star T, then the operator T is said to be normal. So from these definitions, we can clearly say that if an operator is self-adjoint, then it should be normal. Okay. So which is the first intuition which we get from these definitions? So we can formally state that. So the first intuition or first remark is T is self-adjoint implies T is normal. So assume that T is self-adjoint. So which implies T star is equal to T. Since T is self-adjoint implies T star is equal to T. Then T star is equal to T times T, which is T square, which should be equal to T star T, which is T star, which is T square. And T star and T star T is T square. So T star and T star T are actually same. So which implies T is normal. So T self-adjoint implies T is actually normal. And the second intuition which we can get is T is unitary implies T is normal. So T is unitary meaning T star is equal to T inverse. Then T star should be equal to T inverse, which is the identity, and T star T, which should be equal to T inverse T, which is the identity, or T star and T star T should be equal. So, which implies T is normal. So, from the definition itself, we can clearly understand that every self-adjoint operator is normal and every unitary operators are normal. And the converse part may not be actually true. Every normal operators need not be self-adjoint or unitary in general. So we need to have a particular example which establishes that T is normal need not imply T is self-adjoint or T is actually unitary. So we will give a particular example for that. So converse part need not be actually true. So converse need not be true. For we consider an operator, the identity operator, I from H to H, which is the identity operator. And associated with this operator, we define a new operator, which is a bounded linear operator, which is defined as 2IH, where I is the imaginary number. Then clearly, the operator I is actually self-adjoint operator. Okay. Then T is of the form some alpha S. Then T star should be of alpha S star, which by previous definition should be alpha times S star, alpha bar times S star. So T star should be equal to 2I capital I star, which is 2I conjugate times I star. I star is I, 2I conjugate is minus 2I, minus 2I I star. So here T star and T are actually not same. Okay. From that we can clearly say that T is not self-adjoint because T star is minus 2i, T is actually 2i, which is not actually same. Now T star should be equal to 2i minus 2i. So which is actually equal to minus 4 I square. I times I is actually I. So I square is minus 1. Minus 1 times minus 4 is actually 4. So which is actually 4I. Now T star T should be equal to minus 2i times 2i. So which is actually minus 4I square I, which is actually 4I. So T star T and T star are actually same, which implies that T is normal. So this operator is actually normal, but it is not self-adjoint. So every normal operator need not be self-adjoint. Even though every self-adjoint operators are normal, the converse need not be true. The same example can be used to establish that every normal operators need not be unitary. So this operator, which is defined as T is equal to 2i, where I is the identity operator, this is normal. We have already established that. And T star, we have already proved that it is minus 2i capital I, and T inverse is actually 2i capital I inverse, we know that the inverse of the identity operator is identity operator itself. And inverse of 2i is actually minus 1 by 2i. So 2i inverse is actually 1 by 2i, which is actually equal to, so minus 1 by 2i. So this is actually minus 1 by 2i times I inverse is I. So this is actually T inverse. This is T star. So clearly T star not equal to T inverse. So clearly T is not unitary. So this operator is actually normal, which is not unitary. So which implies that every normal operator need not be unitary. So the same example can be used to establish that every normal operator need not be self-adjoint. So even though every self-adjoint or unitary operators are normal, the converse need not be true. So we can conclude the result as every self-adjoint or unitary operators are normal. The converse need not be true. Meaning, every normal operators need not be unitary or self-adjoint.